Hello everyone, I am Honardu. I am currently a PhD scholar at IIT Kanpur. Today we will discuss about fundamental of supersonic and hypersonic flow, week 11th lectures. In week 11, mainly hypersonic test facility, supersonic and hypersonic test facilities, super shock interaction and shock-wave boundary interaction, and hypersonic vehicles were discussed. We will see some problems related to it and we'll see some theory also. First problem: when shock waves and expansion waves reflect from a solid ball of an oblique shocks reflect as expansion fan, expansion fans reflect as expansion fan, oblique shocks reflect as oblique shocks, expansion fans reflect as oblique shocks. What is the answer for this one? Answer for this one will be option B. Expansion fan reflect as expansion fan, and option C. Oblique shocks reflect as oblique shocks. So whenever there is one ball and one shock is sorry whenever there is one ball and one oblique shock is reflecting, then it will reflect as oblique shock only. Its nature will remain same. So whatever wave is reflected from the solid ball, its nature will remain same. And if expansion fan is reflecting from a ball, it will remain expansion fan only. So option B and C are correct. Now we will see the next problem. The following statement or statements is or are true in connection with wave reflections from constant pressure boundary. Previous problem was related to wave reflections from solid boundary. This problem is related to wave reflections from pressure boundaries. Statement 1. A shock wave reflects as an expansion wave when it meets a constant pressure boundary. Statement 2. An expansion fan reflects as a shock wave when it meets a constant pressure boundary. Option A, statement 1 true, statement 2 false. Option B, statement 1 false, statement 2 true. Option C, statement 1 true, statement 2 true. Option D, statement 1 false, statement 2 false. So in this problem we have two statements and we have to tell which one is true and which one is false. And in this statement, one wave is reflecting from constant pressure boundary. In statement 1, a shock wave is reflecting from a constant pressure boundary, and in statement 2, an expansion fan is reflecting from the constant pressure boundary. So in option A, let's say this is a constant pressure boundary, a shock wave is reflecting. So what will happen to it? It will become expansion fan. And If there is expansion fan, it will reflect from the constant pressure only, and what will it become? It will become a shock wave. So if there is reflection from a constant pressure boundary, the shock, the wave will become of the opposite nature. Like shock wave will become expansion wave, and expansion fan will become shock wave. So statement 1 says a shock wave reflects as an expansion wave when it meets a constant pressure boundary. So it is true because nature of shock wave will change to expansion wave when it meets the constant pressure boundary. So this is statement 1 is true. Statement 2 is an expansion fan reflects as a shock wave when it meets a constant pressure boundary. So its nature is also changing. This is also true because expansion fan. Wait a minute. So this statement is also true that expansion fan, when it reflects from a constant pressure boundary, will become a shock wave. So both statements are true. So option C is the correct one. Now we see the next problem. The following statement or statements is or are true in connection with shock interaction as per the Adney's classification. Statement 1. The type 1 interaction involves two shock waves of the same family. Statement 2. Type 4 interaction produces an unsteady supersonic jet impinging on the body. Option A. Statement 1 true, statement 2 false. B. Statement 1 false, statement 2 true. C. Statement 1 true, statement 2 true. D. Statement 1 false, statement 2 false. So this problem is related to shock interaction. Adney has classified this shock interaction in 6 types. And in these two statements, type 1 and type 4 are mentioned. And we have to tell which of these statements are true. So before solving this problem, we will see what are the shock interactions which were defined by Adney, all 6 types. Let's say this is one body. And due to the flow, this is the Bosok is forming here. And this central line is the line which is passing through the stagnation point and center of the body. And there are two sonic points. Sonic point are point at which the flow through the Bosok will be at Mach number equal to 1. So if you see here this region, here Bosok will be strong. So whatever flow passes through it, it will become Mach less than 1 in this region. But this Mach number, as we move away from the stagnation point, this Mach number will increase and we will reach one point where Mach number will be 1. That point is called sonic point. So there are two sonic points on the body. Based on the sonic point, we will define different 6 regions, and if shock will impinge on this region, we will get different type of shock interactions. We will see first type 1 interaction. So type 1 happens between First thing I will tell one more thing. If shock wave is like this, it is called left running wave. So if flow is passing through it due to the shock wave, it will move like this. And if shock wave is like this, then it is called right running wave. If flow is moving like this, it will move in this direction due to this right running wave. This is left running wave, and this is right running wave. So if you see this region, this is almost like right running wave. Okay. So if one shock is incident shock is interacting with it, it will be left running wave. So the nature of in the type 1, it is interaction of two straight oblique shock which are of opposite family. One is left running wave and another is right running wave. So I think in the question it was asked this only, but we'll first learn all other types, then we'll discuss that problem. So it is interaction between two straight oblique shocks of opposite family. The left running shock IS, this I is the incident shock, and this BS is bow shock. So this left running IS interacting with right running BS, and due to which there will be two transmitted shock. One will be this and one will be this, and this will be the flip line between these two. This is the flip line. And the flow will be supersonic everywhere because these are the, you can say, low strength shocks. So flow will be supersonic everywhere in this type 1 interaction. Now we will see type 2 interaction. Someone joined. So currently what I was doing, I was telling about one problem in which it is related to shock interaction. According to Edney's classification, there were two statements. Statement 1, type 1 interaction involves two shocks of the same family, and statement 2, type 4 interaction produces a unsteady supersonic jet and impinging on the body. So before solving this problem, I was telling about different type of interaction. So if this is a blunt body, on the blunt body there will be two sonic points. Sonic point are point around which the flow will change from subsonic to supersonic. Like around, if you see this front part, there will be, it will be a strong bow shock. So a flow across it will be subsonic. But as you move away from the stagnation point, the Mach number will increase, and at one point this Mach number is 1. That point is called the sonic point. So based on the sonic point and the strength of bow shock, we have divided this region into 6 regions. 1, 2, 3, 4, 5, 6. So the type 1 interaction is the interaction between the right running bow shock and left running incident shock. If you see this region, in this region this bow shock is right running. It is almost a straight line and it is a right running. And if there is incident shock, left running incident shock, both will interact and the transmitted shock will be and two shock will be transmitted and there will be one flip line. And as the strength of this bow shock is very less away from the stagnation point, the flow will be supersonic everywhere. This is the type 1 interaction. Now we will see the type 2 interaction. So in the type 2 interaction, one thing is that before in the type 1 interaction, this you can see that this right turning wave angle was also very small, if you see. But in this type 2 interaction, this right turning wave angle is not small, it is bigger. So this bow shock is not almost a straight line, it will be slightly curved. And this angle is crossing the limit of the is crossing the theta max value for the oblique shock, for which the shock will be a straight line. So whenever the shock IF instant shock impinges on this bow shock, and this bow shock, this location, impingement location is just downstream of the sonic point. This is just downstream of the sonic point. And this curved bow shock is stronger at this location, and the local flow Mach number is lower. The flow Mach number will be lower, but it will be greater than 1 only. So there will be transmitted wave, and there will be one Mach line, normal shock, which is called the Mach line. Due to this Mach line, the flow across it will be subsonic. But you know that this bow shock is slightly stronger, so here flow will be the supersonic. So it will create a region in which there will be subsonic flow. For type 1 interaction pattern cannot occur because the flow deflection angle exceeds the maximum allowable by straight oblique shock theory, which I already told that this angle is greater than theta max value. That's why this type 1 interaction will not occur. Consequently, the two interacting shock waves are connected by nearly normal shock, which is the Mach reflection. This is the Mach reflection, which is the normal shock wave. And there is one embedded region. These are the slip lines. These are the two slip lines, and there is one embedded region which is the subsonic, and other region are the supersonic region. So this is the type 2 interaction. And in the type 3 interaction, the bow shock is just upstream of the sonic point, this region. So what will happen that across the bow shock, the flow will be subsonic. Okay, one thing, when these two shocks will interact, there will be two transmitted shocks. So the flow behind the bow shock will be subsonic because it is upstream of the sonic point. but the flow behind this transmitted shock will be greater than uh, will be supersonic. So this slip line so the flow behind the shock bow shock is locally subsonic. The flow behind the bow shock is locally subsonic, and the slip line trails downstream from the interaction point and its impingement on the body. The slip line will impinge on the body, and the slip line separates the locally subsonic flow above it and locally supersonic behind it. So this is the subsonic flow and this is the supersonic flow. The slip line separated, and after it there will be some complex flow patterns. This is the type 3 interaction. Now we will see the type 4 interaction. It occurs when the incident shock impinges on the stronger part of the bow shock at the location usually far upstream of the sonic point. Here in this region where the bow shock is strong and it is far upstream of the sonic point. And in this region, the turning angle of the flow by the body is too large. This turning angle is too large. If flow is coming like this, then this turning angle is very large. For the supersonic flow to be deflected downstream through the attached shock. This was possible for the type 3 interaction. Behind the impingement point of the impinging shock IS and the bow shock BF, a supersonic jet SJ is formed. The supersonic jet SJ is formed, and there is these are bounded by two slip lines. This is a supersonic jet, and these are bounded by two slip lines, and there is the you can say the series of shock wave and expansion fan are here, and it will go and impinge on the body, and it will terminate by the normal shock close to the body surface, and due to which the pressure will be the high and the heating will be higher than the without the impingement case. And it will also be unsteady in nature. The type 4. Now we will see the type 5 interaction. So this shock interaction occurs when the impinging shock IS and bow shock are of the same family. If you see the type 2 interaction, It is somewhat similar to type 2, slight difference only. In type 2, this Bosock and impinging fork are of different nature, left running and right running. But in type 5, both are left running. So there will be one Mach reflection will be there, and the there will be subsonic flow between the two slip lines. The impinging point is just downstream of the sonic point behind the Bosock. It is just downstream, like similar to the case of type 2 interaction. In the type 5 interaction, the two intersecting shock waves are connected by nearly normal shock. They are connected by nearly normal shock. This produces a marked reflection like type 2 interaction. And an embedded subsonic flow region forms downstream from the intersection region. So this embedded subsonic region is formed. Both are bounded by one slip line, and one side there is very thin supersonic jet, and this is very thin, and it acts more like a slip line. This jet is very thin. So this is a type 5 interaction. Type 6 interaction is also similar to type 1 interaction. This is the type 6 interaction. They are similar to type 1 interaction. Only thing is that these interaction involve two left running shock waves, and the impingement point is far downstream from the sonic point. Here you can see this region. It is far downstream from the sonic point. This interaction is analogous to type 1 interaction, which I already told. Here two shock waves of the same family intersect at a point, coalescing into the single transmitted shock and a slip line trailing downstream from the intersecting point. As you can see here. So now we have seen all 6 types of interaction. So we will see now the problem which we were discussing before. So statement 1 was type 1 interaction involves two shocks of the same family, which is what it is, true or false. It will be false, because one is the incident shock is left running and both shock is right running. So both are of opposite family. Statement 2. Type 4 interaction produces an unsteady supersonic jet impinging on the body. This is true. In the type 4, we have seen that it produces an unsteady supersonic jet. This jet is supersonic, which is surrounded by two subsonic regions. It produces one supersonic jet which impinges on the body. So this statement is true. So which option will be correct? It will be option B. Now we will see the soft wave Pondelier interaction. So let's say there is some flow is happening and there was one boundary layer and there is one incident shock which is incoming here. So due to this shock wave, there will be adverse pressure gradient. Let's say this is P1 and this is P2. Then P2 will be greater than P1. So due to this, so there will be adverse pressure gradient. Due to this adverse pressure gradient, there will be flow separation. So adverse pressure gradient across the incident normal or oblique shock causes the boundary layer to separate on the body surface and forms a flow separation bubble. So the flow separation will be there and it will form the bubble. And this separation bubble, if you see here, this separation bubble will act as a ramp and there will be series of compression waves which will coalesce and make a oblique shock. It is called oblique separation shock. So the interaction of this incident shock and separation shocks will create the transmitted shock. And this transmitted shock will penetrate the viscous flow and it will penetrate till this sonic line. This is the sonic line. So this is the viscous flow. So this transmitted shock will not penetrate till the body, because what happens near the body, this flow will be zero. Flow velocity will be zero due to the slip boundary condition, and as we move away from the body, its velocity will increase. So there will come a section where mechanically that section is called the sonic line. So shock will go till sonic line only, and after hitting this sonic line, it will reflect and it will form Prandtl-Meyer expansion. And why the nature of this transmitter shock change? Because there is almost constant pressure in the bubble. So from the constant pressure ball line, if some wave is reflected from it, then its nature will change. That's why there is Prandtl-Meyer expansion. So as there is Prandtl-Meyer expansion, it will cause the shear layer to deflect towards the ball. As it will move towards the ball, this bubble will reattach to the wall, and due to this reattachment, there will be series of compression waves, which will coalesce together and form a detachment shock. This is the shock wave boundary layer interaction on the flat plate. Now we will see some test facilities. For this test facility is shock tube. Generally in shock tube there are two sections. One is driver section and one is driven section. Driver section is filled with high pressure gas and driven section is filled with low pressure gas. And let's say the diverse section condition are denoted by number 4, pressure P4, T4, temperature T4, mu4, A4, gamma 4, and the molecular weight M4. And the for low pressure section, its pressure temperature are P1, T1, mu1, A1, gamma 1, like this. And molecular weight of gas is M1. So and both sections are separated by one diaphragm. So initially the pressure will be like this. This is the distance x. In the diverse section, constant pressure P4, and in the driven section, constant pressure P1, and there will be pressure difference. Now, when this diaphragm bursts, this diaphragm can be burst by many ways. So, if this diaphragm bursts, then what will happen? One normal shock will move towards low pressure section, it means driven section, and one expansion wave will move towards high pressure section. Why will it happen? Because you can see there is pressure difference here. So it will try to make both pressure equal. So lower pressure will be made higher, and higher pressure will be made lower. So pressure can be increased only by a shock wave, and pressure can be decreased by expansion wave. That's why in the driver section, expansion fan will move, and in the driven section, shock wave will move. So one normal shock wave is moving to the right with velocity W related to the laboratory frame of reference, and expansion fan is propagating to the left. And as initial condition of 1 for the driver section, for driven section, and 4 for the driver section. But this shock wave will move with the condition is 2, different condition, and the expansion fan will move this condition is 3. These two conditions are different because both gases are also different. That's why 2 and 3 are different. And there will be a contact surface, which is the interface between driver and driven gas, and it moves to the right with the velocity u2. This contact surface will also move with the velocity u2 related to the laboratory frame of reference. So what will happen? If you see, this is the x, distance along the length of the shock tube, and this is the pressure. If you see here, the pressure here will be same. The condition at the constant contact surface is such that pressure will be the same. For region 2 and 3 will have the same pressure, and velocity of the region 2 and 3 will also be the same. So it will have constant pressure from this region to this region, P3 equal to P2, and this region will have pressure P1, and this region will have pressure, P4, and due to this expansion fan, there will be change in pressure here, and due to the shock wave, this pressure change will be the abrupt. So as this shock wave will move, this pressure P1 will move to the P2, and as this expansion fan move here, this pressure P4 will become P3. I will make one X-ray diagram also, but time what is happening. Let's see, initially diaphragm was here. This is X. Sorry. This is time t, this is x. Initially what was This pressure here was P1. This condition is 1, this is 2 initially. So when diaphragm will burst, one shock wave will move. Shock wave velocity is constant. That's why you can see that with time, let's say there is one shock wave, with time the shock wave will move in this direction, right direction. So shock wave is moving in the right direction. And expansion fan will move in the left direction. Expansion fan is moving in the left direction. And there is one contact surface also, which is moving in the right direction. This is the contact surface. This is the normal shock. And this is the expansion fan. And after it will reflect from the wall, and it will be like this. So initial condition, what was the initial condition? 1 in the driven gas, and driven it was 4. When it is processed by shock wave, what will condition will become? 2. After processed by shock wave, its condition became 2. And this in the driver section, if it after it is processed by expansion fan, its condition became 3. And both 2 and 3 are separated by contact surface. Like this, we make the XT diagram. XT diagram shows how shock waves and expansion fans are moving, and how are the conditions of gases changing with respect to distance and time. This is for the shock tube. We have seen here that this is the high pressure section and this is the low pressure section. But how do we fill this pressure 4 and 1? First, that we get some condition, like we get some shock strength. For this, if we solve these equations, if you, let's say this is normal shock wave, you can use the normal shock relation here. This is expansion fan, you can use the isotropic relation here. And we can use the pressure and velocity equal for contact surface. If we use all these relations, we will get relation of P2 by P4 by P1 as a function of gamma 1, gamma 4, A1, A4 and P2 by P1. And if you plot this from this relation, we can get that this A1 by A4 should be smaller. For a given P4 by P1, for high value of P2 by P1, A1 by A4 should be smaller. So what is the A1 by A4? If you see this, A1 is gamma 1, R1, T1. A4 is gamma 1, R2, T2. And R1 can be written as gamma 1 R bar. R bar is universal gas constant upon M1. M1 bar is molecular weight. Sorry, this is 4. Gamma 4 R bar upon M4 bar T. So it will give gamma 1 T1 M4 upon gamma 4 M1 bar T4. So if you can see that one more thing to tell, if we want to test, let's say, some model, so generally in the soft tube this end is open, so whenever our gas will move, this section, this part is open, so we can keep our model here, and after this the region between this and this can be taken as test gas. And what happened with this test gas is measured. So this 2 is the test gas. And 2 and 1 are the same gas. So you can say that 1 and 2 are have the same molecular weight. So generally this test gas is air only, atmosphere. So M1 we cannot change, gamma 4 we cannot change. Only thing we can change is gamma 1, T1, M4 and T4. And M4 bar is nothing but molecular weight of driver gas. So if we have low molecular weight gas in the driver, it will have lower value of A1 by A4. So that's why generally we use helium or hydrogen as a driver gas, as it is very hazardous to use the hydrogen because it reacts with oxygen very easily. That's why generally helium is used. We can also increase the T4 also. If we increase the T4, then A1 by A4 will also be smaller. That's why generally driver gas is preheated before using. This is the working of soft tube. Now we will see the reflected soft tube. In the soft tube, this end was open, so this soft tube did not reflect. But let's say this end is roll. Then what will happen? This soft tube will come and hit the roll. But let's say this soft tube when is vanishing after the hitting the wall. And what will happen? There will be some velocity at the wall also. And when this soft tube reaches here, there will be some flow velocity at the wall also, which is not possible. Because at the wall, this velocity should be 0. That's why the soft wave will reflect. So when the soft wave will reflect, the velocity behind the soft wave will be 0. And this condition is named phi. And it will create the stagnation region here. You will get some stagnation gas, and this gas can be used gas can be used in different ways, like the radiation study can be done for this gas, what are the chemical species present, this type of study can be done for this gas, or this gas This region can act very simply as a reservoir for the reflected soft tunnel also. So X-ray diagram, it is the same as before, only thing is that there was diagram. And it is here there is wall. So it will reflect from the wall. So this region was 1, this was 2, and from the reflected from the wall, this region became 1. This is the X-ray diagram. And in this case, our test gas will be in the region 5. So for utilizing this gas, we use the one nozzle, this and one secondary diaphragm, so that this gas can be expanded further. This is called reflected shock tunnel. So in reflected shock tunnel, in this region, this end wall, we use one another secondary diaphragm, and after that we use the nozzle, and after that there will be one test section and one dump tank. So what will happen that just behind the reflected shock wave there will be high pressure, high temperature gas. Due to this high temperature and high pressure gas, the secondary diaphragm will burst. And when this second diaphragm will burst, high pressure and temperature gas will be expanded through this nozzle. And this expanded gas will be used as a test gas in the test section. This is the working principle of reflected shock tunnel. So one thing I told you before, that we can heat the driver gas also. So for the heating of the driver gas, there are different ways. One of the ways is combustion type. The driver gas is combust. Other is electric arc type. So like this, different type of shock tube are made. Combustion type shock tube, electric arc type. One is the free piston type. In free piston type, this driver gas is compressed by a piston. So the compressed gas will have high pressure and temperature. That high pressure and temperature gas will be used for bursting the diaphragm. There is all conventional type. In conventional type, we don't heat the gas, we directly fill the high pressure gas and it will be used for bursting the diaphragm. And there is also one detonation type, where we use the detonation wave to heat the gas. This is the fourth shock tube. There is and this shock tube, reflected shock tube, are impulse facility. In impulse facility, we get the test time of the order of millisecond or sometimes microsecond also. And due to this test time being less, we can generate the flow corresponding to the entry. Otherwise, for the very long time, it is not possible to generate this flow to the structural strength of the material. There is also one more type of impulse facility, which is called expansion tunnel. An expansion tunnel, after this driven section, there will be secondary diaphragm here, and after the driven section, there will be one more section which is called explanation tube. So, which is kept at a lower pressure than this low pressure section, and due to this low pressure, then when the secondary diaphragm will burst, there will be an slow expansion there. There will be an slow expansion of this driven section, due to which this gas is further accelerated, and which will create a much higher enthalpy flow than compared to soft tube and reflected soft tube. As it was not in the course, I am not telling about that more. One thing now we will see, pressure deflection diagram. Let's say there is one oblique shock, there is one Mach number m1, and it will become m2, and this flow is deflected by an angle theta. Here the pressure was P1 and here pressure was P2. Let's say pressure P1 for Mach number m1, we need a P theta diagram. This is for left running wave, this theta will be positive, and this is for left running wave. If there is right running wave, this theta was negative. So this is for m1. So if we keep this theta as different deflection angle, if we keep changing the deflection angle, then we will get a different P2 value. Using this P2 and theta value, we plot this pressure deflection diagram, and this is the theta max value. So in this figure, for angle theta, this will be the point P2, and let's say this is P2 dash. Then this will be the 2 dash point we will get. This is the pressure deflection diagram. It is useful for studying the shock-shock interaction. One example you will see. So this is angle theta1, and this is angle theta2. There will be one oblique shock here and one oblique shock here. Both will interact. And there will be this decline. So this flow was m1 coming with m1 Mach number. Due to this theta1 angle, it got deflected by theta 1 angle, and due to this transmitted shock it got again deflected and at angle phi. Let's say this angle was phi. Similarly, on the top part, due to this theta 2 weight, this get deflected by theta 2 angle, and again using the transmitted shock it reflected by the overall angle phi. Now we will see the Pfeffer deflection diagram. Initially, let's say this Pfeffer was P1. Across this theta 1, the Pfeffer became P2. Across, due to this theta 2, this Pfeffer became P2 dash. And again, this Pfeffer became P3 here and P4 here. At the flip line, this P3 will become equal to P4. So first for P1 and M1, we make one Pfeffer deflection diagram. So at the theta 1 angle, we get this point 2, this point was 1, we get this point 2, and at this theta 2 angle, we get this point 2 dash. This one was for Mach number M1. Now at point 2 with Mach number M2, this Mach number is M2. With Mach number M2, we made one Pfeffer deflection diagram again. This is for Mach number M2 and was made with Pfeffer P2. Similarly, with P2 dash, we made one Pfeffer deflection diagram for Mach number M2 dash. This Mach number is M2 dash. The Pfeffer was P2 dash. So we have seen that this Pfeffer at flip line will be equal to P3 and P4 will be equal. So these two curves would intersect, and these two are intersecting at this point. So we take this as 1, 3 and 4, and it will come angle 5. Like this, we can find what is the pressure and what will be the net deflection angle. Like this, it is used to solve shock interaction problems. One last thing we'll see. One is hypersonic gliding. And let's say one re-entry is happening at a curved path. Whose radius is r. And at this point there is one glider. There is one glider. It has weight W. This angle is theta. The lift here is L and drag is D. If we resolve this weight, then this component will get W cos theta, and this component will get as W sin theta. So we'll write the F relation here is dV by dt. So we'll write the Gaussian equation. Along the drag direction, the forces will be W sin theta minus D equal to m dV by dt. M is the mass of glider. And along this direction, the forces should be L minus W cos theta equal to m V square upon R. And as it is gliding, we can assume that theta is very less. So we can write sin theta approximately as 0 and cos theta is 1. Then we will get equation minus D equal to m dV by dt and L minus W equal to m V square upon R. If we take this equation, then D can be written as rho V square S half rho V square S into CD. Equal to W upon G, mass we can write weight upon G, dV by dt. Or it can be written as minus 1 by 2 rho V square equal to W upon CDS 1 by G dV upon dt. Here this W by CDS is called ballistic coefficient. Similarly, this L minus W m V square upon R, L can be written as half rho V square S CL minus W equal to W by G V square upon R. Similarly, we can divide it by SCL. We will get half rho V square minus W by CLS equal to W by CLS 1 by G V square upon R. This W by CLS is called lift entry coefficient. Or you can say lift parameter. So in the design of some hypersonic vehicle, these two parameters are important. Either the lift parameter or ballistics coefficient. It is used for designing the vehicle. In the class, it was also taught about the hypersonic wind facilities, and these hypersonic wind facilities generally depends on nozzle. That part make number nozzle you want to use. Accordingly, it should be made. So for today, we will stop our class here. Thank you.